That's about it. So the question reads: from a telecommunications point of view, it's advantageous for satellites to remain at the same location relative to a location on Earth. This can occur only if the satellite's orbital period is the same as the Earth's period of rotation. So you know that the Earth rotates around its own axis, right? So that is 24 hours. So the main reason why I'm making note of that is because someone can mistaken that period to be the time it takes for it to go around the sun. So that's not what that is talking about. Huh? It's rotation of the Earth's rotation, right? So yeah, approximately 24 hours that they've indicated. At what distance from the center of the Earth can this geosynchronous? So geosynchronous simply means that it's moving at the same pace with the Earth. It's in sync with the Earth. Okay. So I'm just trying to explain this thing so that we can understand the question. Okay, can orbit be found? What is the orbital speed of the satellite? So really, with these questions, it's all pretty much about the understanding of the formulae and making use of them. So what we are going to use, we're going to use the equation from Kepler's third law. So that's the equation. So what then we just have to do here is, what are we finding? We are solving for r. Okay, so what then do we have? So the mass, that's for the mass of the Earth. So here we are using the mass of the Earth, but you know that Kepler's this law was formed on the basis using the sun, right? But this orbit is not rotating around the sun. So here we are now specifying this question to what? To the Earth, okay? Because this orbit is this satellite will be orbiting around the Earth. Okay, so we've done that. Then what else do we need? What's the period? Remember, period yesterday we said that's T, right? And they've told us it's 24 hours. That's the time the Earth takes to rotate about its own axis. Now we always use seconds in physics. So how do we convert this? We say, what do we want to cancel? We want to cancel hours. So minutes should be on top. Then we want to cancel minutes, so seconds must be on top and then 1 minute be down. So once you do this calculation, you are going to find the seconds, the number of seconds that we are going to use in our question. So these are the number of seconds which are in a day. So what's happening here is, you cancel that, you cancel that, you cancel that, you cancel that. You are remaining with what? With seconds. So when, and then the mass of the Earth, it will be given to you. So the mass of the Earth, it will be given to you. So pretty much the only thing which you are doing is just substituting, to be honest. So what you are going to have is the mass of the Earth. It's 5.98 times 10 to power 24 kg. Okay, then our G is going to be 6.67 times 10 to power 11, negative 11 plus kg negative. So with those values, what you just do is just substitute, really. So you do the substitution in this equation. So the T, which is the period, of course, that's That's that seconds. Then you're going to have 4 pi squared over, okay, let me write this properly. So 4 pi squared, so that's pi. Then mass, or sorry, g, that's seconds squared. Then mass of the earth, okay. Okay, so remembering that all this is over that. Okay, then there we've got r. So the best way to do it, find the answers on the left and on the right. Then you just divide. Then the answer you get, you do the cube root. Then you are going to get, so you are going to get that value, isn't it? So that is the distance that this orbit has, or this satellite rather, has to be away from the earth for it to be able to manage this. Then the other thing is, what are we then solving? What is the orbital speed of the satellite? So you may want to remember that how do we find this period? We found this period by saying speed, okay? Speed is distance over the period, isn't it? Okay, because now we're now looking at about we're looking on the satellite. So this particular satellite will be rotating, or will be having a period the same as the Earth when it's rotating about its own axis, isn't it? Because they are saying this will be a geosynchronous satellite. So it will be moving at the same pace as the Earth, so that anytime when you want to look at it, it's going to be at the same position because it's moving at the same point with the one, or it's moving at the same rate with the Earth, isn't it? So then we say this equation, then we know that the distance we are talking about is the circumference, okay? The circumference around the structure, which in this case is the Earth. We know that that circumference is the same as 2 pi r, 2 pi r, which is going to be over that. So we just change that d to 2 pi r. And once we have got this, it's a done deal. We write our 2 pi, then the r that we found on top, and then we've got uh, the period. The period, then the speed is going to be, so this should be the speed of the satellite, okay? So that should be the speed of the satellite. So really, with these questions and on this topic, it's pretty much about just, okay, let me write this one properly. So it's just pretty much about understanding the terms and knowing the formula, to be honest, because once you know the formula, you see that here we're just replacing and just understanding uh the question. So that's what's important. So then that's the end of this topic. So now let's start rotational equilibrium. So really, when we're talking about rotational equilibrium, it's very important because you may remember that the time when we are looking at the time when we were looking at forces, we are not really caring much where the force was being applied. Okay, for us it was just yes, the force is acting on this object, but then it's very, very important for us to actually know where the force is being applied. Okay, so I think that's something that's very, very important to take note of. So having done that, so when it comes to this topic, we are then going to be concerned about where is the force being applied. And so when we talk about a force we know from Newton's second law that is going to produce an acceleration, right? But then torque, okay, torque, that's something we'll be talking about. Torque causes angular acceleration, and there is actually a relationship between these two things. So look at this example that's on our far right. Anyway, let me just zoom it. So what is torque? Torque is the product of the radius times the force. Okay, so it's going to cause this hinge. So you can see this hinge. So think of, so this is a door that's being seen from on top. Okay, so this is a door that's being seen from on top, right? And so that hinge, that's where the door opens from. And so when this person then is trying to open this door, they are going to use a certain force, right? And this force is going to be applied at the door handle. Now the door handle is going to be some radius, some distance, okay, away from the what, away from the point O, or the point of rotation. So then what's going to happen is that when this is happening, then it's going to cause what, an angular acceleration. It's going to cause what we call now the product of this radius, of this distance, or we can call it distance, the so the product of this distance and the force applied to produce an angular acceleration, that is what we call torque. Okay, so that's something that's important to take note of. So torque is equal to, like I've said, it's a product of that distance, the length of the position vector, r, so that is the length, and then the magnitude of the force being applied, that's force. So meaning the units are going to be force times what, force times r, isn't it? So yeah, so that's how we go about that. So have we understood the concept of torque? Does anyone have a question? Okay. Okay, so having done this, okay, so yeah, so that's it. Now we know that this particular angle, there's something that's interesting about torque. You see that in this particular question, this particular diagram, you see that there is nothing much that can change about the distance, right? About the length from the point O to where the force is being applied. But one thing that's going to happen is that when, okay, or rather we can say, if, okay, let me put it this way, if we change the length and maintain the force, the torque is going to change. If we change the force and the distance remains the same, the torque is going to change, right? So that's an important point I wanted to bring across. Now if we now assume that the if we then assume that the force is the same, okay, so let's say we are trying to do something, and then we say, okay, let's maintain the force, let the force that's being applied be the same, and let's just change the point at which the force is being applied. So if we change the point at which the force is being applied, what's going to happen then is that as we increase the r, okay, the point from which the force is being applied, the torque is going to increase as well. Try to think of this logically. If look at this spanner, yeah, this spanner that they are showing us here. See that if you hold this spanner where the blue arrow is, it will be difficult for you to screw, isn't it? It will be difficult for you to screw because the amount of torque that will be producing will be small. But the same force, if we then apply it a little bit distant from this point O, you see that our torque increases. And finally, that's why whenever someone is screwing something, they want to touch the spanner where towards the end. And you can even think of it logically. That's why even when they are making a door, they make the handle to be as far away from the hinges. Okay, and that's why you notice that opening a door from the middle is hard to do because even though you may be applying the same force, but the torque you are producing is less because your distance from the hinges is what is less. Okay, so that's an important point to take note of. So, remember what when we were looking at angular motion, we said counterclockwise is taken to be positive. So what's counterclockwise? Counterclockwise simply means going against the watch or the yeah going against the clock. Okay, so that's counterclockwise. So in angular motion, uh, when something is going counterclockwise, then it's actually positive. Okay, so that's something that's very, very important to take note of. Okay, okay, so that's something that's important to take note of. Are there any questions? Okay, so that's about it, right? So if net torque, okay, so when the force causes the object to rotate clockwise, the torque on the object is going to be negative. Okay, when two or more torques are acting on an object at rest, the torques are going to be added. Then the same thing like force, right? If the net force is non-zero, let's say it's not zero, what does that tell us? It tells us that there is going to be an acceleration. So the same thing, if the net torque is not zero, what then happens is that the object is going to start rotating at an ever increasing rate. Okay, so there's that acceleration that's going to be there. So the velocity is going to be increasing. As the velocity is increasing, then the angular acceleration is there. Okay, then if the net torque is zero, the object's rate of rotation doesn't change because there is no angular acceleration. Huh? Then these considerations lead to the rotational analog of the first law. The rate of rotation of an object does not change unless the object is acted on by a net torque. Remember the Newton's first law, which says an object continues at constant velocity unless or until it's actually acted upon. Not really acted upon, but you can actually better put it to say until a net torque is applied. Okay, so look at a door. The door will remain closed until someone opens it. But if someone stands outside the door and someone is inside, and both people are so there's one who's pushing on the door, and someone who's pulling on the door. What's then going to so someone is trying to open it and someone is trying to close it, right? You will see that if they're applying the same torque, the door will remain closed. So that's the principle there. So let's just look at this example so that we can be able to appreciate these amazing, wonderful concepts. So, having done that, let's now look at this example, which is just basically going to help us appreciate the importance of knowing counterclockwise and how these things affect our torque values. So then, we've got this wonderful example. We've not yet read the exam. So, two disgruntled business people are trying to use a revolving door. So you see those doors which where someone has to press this side and someone presses this side, as in figure 8.3. The woman on the left exerts a force of 625 newtons perpendicular to the door. So that perpendicular is important because then it tells you that this force is being applied in all its entirety. Okay, in short, it's not being divided into any vectors, horizontal or what's this, right? So it's just that particular force. And so the woman on the left is applying that force perpendicular to the door and 1.2 meters from the hub center, while the man on the right enters, or rather exerts, a force of 850 newtons perpendicular to the door and zero point 0.8 meters from the hub center. Find the net torque on the revolving door. So the other way that they could ask is, who's going to open the door? Or on which side is the door going to be opened to? So one thing that you first want to understand is, let's look at the woman first. The woman is where? The woman is on the left, isn't it? So what happens when she's applying her torque? What's going to happen is that this force is going to force the door to open going this direction. Okay, and this direction is going to be what? Is going to be clockwise, because that's how a clock moves, isn't it? That's how a clock moves. So meaning that the torque for this woman is going to be what? It's going to be negative, because the torque that she's applying, it's to open the door in this direction, right? To move the door in a clockwise fashion. But then for this man on the right, when he's applying his torque, you know, is to move the door where there. So it's to move the door anti-clockwise, which is the same as counterclockwise, or counterclockwise. Okay, exactly. Yeah. So that's the key thing. So this means that this torque is going to be what? Is positive. Now this part is very, very important. Very, very important. So having done that, we can now look at the question. So we know that for the woman, we know that her torque is going to be negative for the reasons that we've talked about. So torque, okay, this symbol can be tricky at times, but let's just write it where we see anyway. But it should be like a T, but it's a funny kind of T though. Anyway, let's write it like that. So torque, so we know that it's going to be negative because it's going to move the door clockwise. So then we're going to have for her, let's say R1 and force 1. So this is going to be negative. Then the distance from the hinge of the door, it's going to be 1.2 meters. So 1.2 meters times, then what's the force? The force is 625 newton. It's going to be uh, negative 750. Isn't it newtons meter? Remember, that's the unit. Huh? So that's for the woman. Then for the man, so we can put like a W for the woman, then the M for the man. Then for the man, we know it's going to be a positive one, because when he opens the door, because the torque he is providing, it's to open the door where? It's to open the door in the counterclockwise. Huh? So you're going to have 680. Okay, so we found that. Then what's net? Net is simply adding these two. So the net torque is going to be, so we're adding. So I'm sure we've seen that from this example, we've seen just how important it is to get the signs uh, accurate. Okay, so that's something that's important there. So we are building up with the questions. Yeah. So then now something that's important, we've been looking at the questions that we've been looking at, and you see that the force that's being talked about is that force which is acting at the perpendicular uh, to the hinges, right? So there is we could say uh, the angle really there. Of course, the angle there we are not putting it into consideration, and it's because, like you would see, for anyway, don't worry, we'll look at that later on. But yeah, so the applied force isn't always going to be perpendicular to the position vector. So that's why you're going to find certain forces are going to be at an angle. So because certain forces are going to be at an angle, we have to be able to form a formula, or to be able to modify our formula for torque in such a way that it can accommodate in the cases where we have an angle. Okay, so what do we do then? You will realize that when we, let's zero in on this one. So then you ask yourself, which component of this force is actually going to, which component of this force is actually going to produce the torque? So we know that torque is going to be there when there is a force which is what? Which is acting in this direction, isn't it? So what then we are asking ourselves is that this force, it's going at an angle of 30. So what we do is we say what is its value there and what's its value there. Then we know that it's this value here, the one that I've circled, is the one that's going to provide the torque. So what do we do using trigonometry? That's going to be what? That's going to be sine theta, then it's going to be opposite, that's that particular side. So let's just, for lack of a better substitution, let's just make it x, no, let's just make it y, since it's vertical. Let's just give it fy, to say that it's a vertical component. Then uh hypotenuse is going to be f, so meaning that force component that's vertical is going to be force times sine theta. So now what this particular what this means is that even though this force is all of it, but the component of it that's going to produce a torque, it's that component of the force that is the vertical component, isn't it? So that's the one that's going to produce the torque. So that's something that we should take note of. Okay, are there any questions? Okay, so that's that. So using this formula, so from what I've explained, so that's where this formula comes in, right? You've seen that formula which has got the torque is equals to r. So the r is still the length remains the same. Then that sine is sine theta is because of what I've explained earlier on. Then now there is an important thing which we call the lever arm. So okay, great, that's good to hear. I'm glad that it's clear. So then there is something that we call the lever arm. So there are going to be certain questions where they are going to give you the lever arm and then they want you to solve. Okay, so they may not give you the R, but they'll just give you the angle, or maybe they'll just give you the lever arm. So what is the lever arm? So the lever arm, if you want to put it that way. So the lever arm is this one. So let's look at it in this way. So basically what you're trying to look at is this. If you look at this as your angle, right? So basically what you're doing, this force has been done at an angle, but then you know that when you draw a line that's going like that, and another one which is extending from there. So basically what you're doing is, to find the lever arm, you are extending this force that's being applied, you are extending it downwards, right? And then you are drawing a line from your point of reference. So our point of reference is this big line. From the point of reference up to this point, you make a what? Perpendicular to the force. So that distance that you find, that's our lever arm. How do we find it? You know that this angle and this angle are going to be the same. So we are going to say, let's use Pythagoras. That's going to be sine. So it says sine theta is going to be what's opposite? Opposite is D. That's our D, the lever arm. Then what's the hypotenuse? R, isn't it? So then you're going to get D is going to be R sine theta. So you see, so that's basically where the lever arm comes in. I hope everyone is comfortable with that. So now we can proceed to then look at a couple of examples. But before that, let's just yeah. So that's talking about the lever arm. So and then again, another thing that's important with torques is that it matters. It very much matters where your what this is. Uh, which part you choose to be your axis of rotation. Okay, so that's something that's very very important to take note of. So you can, so the value of torque is going to depend on the chosen axis of rotation. But if you are solving, let's say a question that has got multiple and like you have to solve multiple torques, it's very very important that once you decide to use one particular point, okay, once you decide to use one particular point as your point where the rotation is occurring, don't change it. The same way we were doing for the potential energy, right? Once we figure out that our potential energy reference value or reference level is, let's say, the ground, we would not change, we would use the ground as our reference value till that question was done. So that's basically the same about talks. Okay, and then here they're just trying to explain that you could either use that angle there or that angle there, but the best way you can do is always use the angle that is between the your R and between your force. But other people can use either way, and like it says here, it's going to be the same. Okay, so that's something important to take note of. So having done this, let's now look at this question. I feel it's going to bring out a number of wonderful concepts that we've gathered up so far. So the question reads, a man applies a force of 300 newtons at an angle of 60 degrees at the door of figure 8.7a, 2 meters from well-oiled hinges. Find the torque on the door, choosing the position of the hinges as the axis of rotation. So you see, for this particular question, they've given us the axis of rotation. Okay, so it will be the hinges of the door. B, suppose a wedge is placed 1.5 meters from the hinges on the other side of the door. What minimum force must the wedge exert so that the force applied in part A won't open the door. So what is a wedge? I'm sure we've all experienced that trouble where you are trying to open the door, just to, like, you don't want the door to be so wide, but you want it to be open to a certain degree. Okay, so there are those door stoppers, we call it a wedge. So it's going to be like a wedge which you just place under the door, and it's going to be holding the door between the door and the floor. Okay, so that's basically what they're talking about. So the first thing we're going to do, we are going to find the torque that's being applied by this particular force. Then once we've done that, then we're now going to find what amount of torque do we need to actually resist this door. Okay, and then also we've taken note of the wedge, so we have to take into consideration the distance and also at what angle is the wedge acting at. So, with these wonderful questions in mind, we can proceed to answer this question. So, Don, I'm going to write a schematic diagram for us so we can be able to follow the question through. So, what they are saying is uh, these are the hinges, and then this is the door handle. So, the force is being applied at this angle. Okay, let me put dotted lines. So that, right? And the force is okay. So you see, so that's the force that's being applied. Then the distance is that 2 meters, right? So they've given us that, and this is these are where the hinges are. So the first question is really pretty straightforward. We are just looking for uh the what's this? We are basically looking for the torque that's going to be applied on this door by that force. So we know now that the force which is going to be important is actually this one, right? The one that's perpendicular to the axis, right? So that's the one that's going to be very, very crucial in this context. So then what we are going to do then is we are going to say torque. So we are going to say torque is R force sine theta. Then our R is 2.0 meters. Then our force is 300 newtons. Then our sine is going to be 60 degrees. Then we calculate our torque. It's going to be okay. So 300 then 60. So our value is going to be 520 Newton meter. Now the question to ask yourself, is it positive or negative? It's going to be positive because remember, it's going to take the door where counterclockwise, right? So it's a positive torque. So having done that, then we are going to have then now the second question. Now they've put a wedge. Now the question that we have to ask is, if you don't want this door to open, then where do you put the hedge exactly? So it's placed on the other side of the door, and it's placed at 1.5 meters. So 1.5 could be somewhere there. So that's 1.5 meters. So that's 1.5 meters, right? So with 1.5 meters there, Then what then you're going to do is, so that's where the way that's where the wedge is. Now you are trying to think of what angle is it acting on. So the angle, remember, for torques it's always going to be what? Perpendicular. Okay, so meaning it's going to be acting perpendicular to the door, because remember the aim of the wedge is to ensure that the door doesn't what? To ensure that the door doesn't open. So it means that this particular torque, look at it, you realize that the angle is what? That angle is going to be negative, okay? Because remember we always use the positive x-axis, right? So if you use the positive x-axis, this angle you would call it negative what? Negative 90. Or if you want, so look at it, when you call it whether you call it negative 90 or you call it 270, you are still getting the same value. Okay, so when you just move from the positive x-axis going down, it's negative 90, but then when you choose to go around, it's going to be 270, but it's still the same value, and it's giving you a negative value, right? Which agrees with the fact that this has to be a negative torque. So I hope that's clear on that part. So then we are calculating the what? We're trying to find what force should be applied, or the force that's the minimum force that the wedge should exert so that the door doesn't open. Now, if the door doesn't open, what does it tell us? It tells us that the net torque is what? Is zero, because it's only when the net torque is zero that there's not going to be a movement in the door, isn't it? So that's what we are looking at. So what we are going to say is that we are going to say net torque is zero. Then we then want to write, and we then want to understand and say, so to say what torques were actually acting on this particular door. So you know that you could have, so if this is the door, the handle is here, we know that there is a force at this point, one. We know that there is a wedge at this point, two. And also the hinges here, though for the hinges it's going to be zero, isn't it? But yeah, but you can put three as well. But it's going to be zero because there is no error, isn't it? There could be a force, there couldn't be a force, but the fact that error is zero, the distance from the point of rotation is zero. So then you don't expect to have a value. So then what you do then, you're going to say torque for the hinge or at the hinge. Then you're going to say torque of the wedge, which is that two there. They are the angle two. Then torque for the force that was being applied by the person wanted. The net has to be what? Has to be zero. Why are we saying zero? Because the door doesn't have to open. Okay? So we're trying to find the force. So we know that for the hinge it's going to be zero by definition because R is zero. Then for this now, for the wedge, we are going to say force, yes, that's what we're trying to find. Then what's the R? The distance is 1.5 meters away from the point of rotation. Then we also have what angle? So the angle is sine negative 90. So you can either say negative 90, or you can say 270. And I've explained why previously. So then what's the torque of the force? That what was the torque produced by the force that we had looked at earlier on? We found that to be 520 Newton per meter. So zero there, right? Then what you do then, you then, so from here really it's just about arithmetics. So here it's really just about arithmetics. So what you're going to do is you're going to say sine negative 90, you know that's negative 1. So negative 1 times 1.5, so that's negative 1.5. That's, oh sorry, that's meter. Don't have Newton, it's meter. Then that's the force. Then when we take this 520 to the other side, it's going to be negative 520 Newton meter over 1.5 meters over negative 1.5 meters. You cancel that, you cancel that. You're going to say uh, negative 520 1.5. That's going to be what? 346.66. Sorry, just put it 347. Since it was 346.66, just put it 3.47 Newton. So pretty much that's how uh you answer this question. So the key thing is to just understand what is being meant, and then to also understand what's being meant by the wage and what's the wage doing, and then to also understand the angle at which uh, the forces are being applied. So that's something important. So now let's now talk about torque and the two conditions for equilibrium. So we know we discussed equilibrium when we were looking at forces, and we simply said this is where the sum of uh, the net the net forces have to be zero, isn't it? That was when we were talking about forces and equilibrium. So we said for something to be in equilibrium, it's it should be that the net external forces are zero. So what does this mean? It can either mean no forces are acting on it, or it can actually mean there are forces that are acting on it, but when you add all of them, they are resulting to zero. That makes sense, right? And then now, because we are now looking at torque, we can now actually add on something to say, because now we know that it's not only a force that can be there, but also torque can also have its own implications. So the first one about force, that's the statement of translational equilibrium. Okay, so it's about something moving and everything. But then the second one, which says the net external torque must be zero, it's about rotational equilibrium. This means that if an object is not to be rotating, it means that the external net torques have to be zero. So this simply means that you could be rotating. Let's say you've got, like the example I gave about a door. Someone is trying to open, someone is closing it. At the end of the day, what happens? The door doesn't open. What? Why? Because even though the external forces are there, but the sum of them are zero. So there is no rotation that's happening. Therefore, that particular object, the door in this example, is in what we would call a rotational equilibrium. So when an object has got both these two things, has got a net external force being zero, has got the net external torque being zero, we then say that it's in mechanical equilibrium. And then we can, because we can choose any location for calculating torques, it's very important that as we are choosing these points, we choose points where certain talks are going to be zero. At least we want maybe one, or maybe at least one or two, at least one talk to be zero, because it's going to simplify an equation. So you can, since we know that you can choose any location, right, to be your point of reference. But whenever you are calculating, you always endeavor to ensure that you choose a particular point where certain torques are going to be zero. That way you simplify your equation. So let's look at this example. A woman of mass 55 kg sits on the left end of a seesaw, a plank of length 4 meters, pivoted as the middle as in figure 8.8. So the middle part is very important because they are telling you that this is actually put where at 2 meters. So that's very important. So it's being able to also pick out certain information like this in the question. It's very, very important. So having done that, okay. So next time we'll look at this particular question. So otherwise, that's about it. I don't know if there are any questions. If not, then we can